A Hamiltonian circuit, also called a Hamiltonian cycle, is a special kind of loop in a graph. Imagine a map of cities, the vertices connected by roads, the edges. A Hamiltonian circuit is a route that starts at a city, visits every other city exactly once, and then returns to the starting city. Formally, for an undirected graph G equals V, E, a Hamiltonian circuit is a sequence of distinct vertices V sub 1 through V sub n such that each consecutive pair V sub I and V sub I plus 1 is an edge in E. V sub n is connected back to V sub 1, and the set of vertices V sub 1 through V sub n equals V. In a directed graph, the direction of each edge must also be respected. The word Hamiltonian honors Sir William Rowan Hamilton, who imagined a Hamiltonian puzzle of moving a horse across a chessboard, visiting each square once. Recursive backtracking builds the Hamiltonian circuit step by step, like a child adding one bead to a necklace at a time. The algorithm keeps a current partial path P equals V sub 1, V sub 2, up to V sub k. At each recursive call, it tries to add a new vertex V sub k plus 1 that is adjacent to V sub k and has not been used before. The state space is the set of all possible partial paths. Each node in this tree represents a different choice of the next vertex. The recursion depth never exceeds the size of V because after we have placed the size of V vertices, we either succeeded, the last vertex also connects to the start, or we backtrack and remove the last vertex to try a different road. The backtrack step restores the previous state, just like undoing a move in a puzzle. Pruning is the art of cutting off branches of the search tree that can never lead to a solution, saving time. Two simple checks are: 1 degree constraint. If any unused vertex has degree less than 2 or less than 1 in a directed graph, it cannot be part of a Hamiltonian cycle because we need at least one edge to enter and one to leave it. 2 connectivity check. After removing the vertices already in the partial path, the remaining graph must stay connected, otherwise, some vertices are isolated and can never be reached. Think of a maze. If a wall blocks off a region, you know you cannot finish the tour, so you stop exploring that direction. These checks are cheap to compute and often prune huge parts of the tree. Branch and bound adds a bound, an optimistic estimate to decide early if a branch can be ignored. One common bound for Hamiltonian cycles is the length of the shortest possible tour in weighted graphs. If the current partial path already costs more than the best known complete tour, we stop exploring it. Another heuristic is to order the next vertices by the smallest degree first, the least constraining rule. By trying the hardest choices early, we either find a good solution quickly, tightening the bound, or discover that difficult branches are impossible, allowing us to cut them off. It is like a kid trying the hardest puzzle piece first. If it fits, the rest becomes easier, otherwise they discard that arrangement early. The Hamiltonian circuit problem is NP-complete, which means no algorithm is known that solves every instance in polynomial time. The backtracking algorithm explores at most big O of n factorial permutations of the vertices, where n equals v. In the worst case, a complete graph where every ordering is a valid tour, the algorithm still tries every permutation, giving a time bound of theta of n factorial. Pruning can reduce the practical cost, but the theoretical worst case remains factorial. Space usage is big O of n for the recursion stack and the current path, plus big O of n for bookkeeping arrays, visited flags. Consider a simple undirected graph with 5 vertices A, B, C, D, E, and edges. A dash B, a dash C, B dash C, B dash D, C dash D, D dash E, E dash A. The goal is to find a Hamiltonian circuit. We start with path P equals A. Step 1, from A we can go to B, C, or E, choose B first branch. Path becomes A, B. Step 2, from B we can go to C or D. A is already used. Choose C, path A, B, C. Step 3, from C we can go to D. A and B used. Path A, B, C, D. Step 4, from D we can go to E. A already used, B and C used. Path A, B, C, D, E. Now we check if E connects back to a yes, edge E dash O exists. So we have a Hamiltonian circuit A dash B dash C dash D dash E dash A. If any choice fails, we backtrack. For example, if at step 2 we had chosen D instead of C, the path would be a B, D, and later we would discover that no unused vertex connects to D without breaking the rules. So we backtrack to try C. The mathematical representation of the search tree shows each node labeled with the current partial sequence. Leaf nodes either succeed, full-length n and edge back to start, or fail, no legal extensions. Function Hamiltonian n cycle G. N equals number of vertices in G. Start equals any vertex, for example 0. Path equals array of size n. Visited equals Boolean array of size n initialized to false. Path 0 equals start. Visited at start equals true. If DFS1 then return path plus start complete cycle. Else return no cycle. Function DFS pose. If pose equals n all vertices placed, check closing edge. Return edge exists path at pose -1 and path 0. For each neighbor v of path at pose -1. If not visited v and degree, constraint OK v and connectivity OK. Path at pose equals v. Visited v equals true. If DFS pose +1 then return true. Visited v equals false, backtrack. Return false. Use adjacency lists for fast neighbor iteration. Keep a global best length variable if working with weighted graphs to apply branch and bound. Implement the degree and connectivity pruning as separate functions for readability. For very small graphs, a bitmask integer to store visited set can be faster. Order neighbors by smallest degree first to improve pruning efficiency. Backtracking is a depth-first exhaustive search, while dynamic programming DP solves problems by storing results of subproblems and reusing them. For Hamiltonian cycles, DP can be done with the Held-Karp algorithm, which runs in big O of n squared times 2 to the n time and big O of n times 2 to the n space. Much better than factorial for moderate n, but still exponential. DP works well when we need the exact optimum of a weighted version. SAT encoding translates the problem into a Boolean formula. Variables x sub I, j indicate that vertex I is in position j of the tour and clauses enforce 1 per row, 1 per column, and edge adjacency. Modern SAT solvers use conflict-driven clause learning and can solve many instances quickly, often faster than plain backtracking. In practice, backtracking is simple to code and works well on tiny graphs or heavily pruned instances. DP is preferable when n less than or equal to 20 to 25, and you need all optimal tour. SAT encodings shine on larger sparse graphs where the SAT solver's heuristics prune aggressively. The choice depends on graph size density and whether you need just a decision yes or no or an optimal weighted tour.